Suppose we start with a positive series, a series of non-negative terms that converges to a sum S. And we form a new series by just rearranging the terms of our original series. So just shuffling around the terms of our series. Every term of the new series will be a term of the original series, but with a different order, potentially different order, and all the terms of the original series will appear in the new series. Okay, so for example, sigma bn we might start with the 10th term a10, then the 3rd, then the 5th, then the 1st, then the 6th, then the 2nd. The claim is that under the assumption that the original series is convergent and is positive, so it's a series of non-negative terms. Remember, positive series is a series of non-negative terms. Then the new series will converge and will converge to the same sum of the original series. The proof is easy. So we take the nth, we consider the nth partial sum of the new series. This is, let's call this Tn. Tn is b1 plus b2 up to bn. But since we have every b appearing here is sum a. So it must be that we must find some integer m such that the mth partial sum of the original series contains all the terms appearing in the nth partial sum of the b's, or the Tn. So for example here, if this is your Bn, and you consider S6 is or T6, the sum of the first 6 terms of the new series, then every term in T6 appears in S10, in the 10th partial sum of the original series. Okay, so Sm has all the terms appearing in Tn plus potentially some others. But because we have a series of non-negative terms, this gives us that this inequality that Tn is less than or equal Sm, and Sm itself is less than or equal the sum S. Because again, you have this positive series of non-negative terms, then the partial sums increase to the sum of the series. Now, from this fact, from this double inequality, we get that Tn is bounded above by S. The partial sums of the new series is bounded above by S, and if you have a positive series whose sum are bounded above, then the series must converge. And they converge to its sum T, that's going to be less than or equal to this upper bound. So T is less than or equal to S. So we get that T is less than or equal to S, but on the other hand, we can also consider the original series as a rearrangement of the new series. And so if we reverse, or if we go through the same reasoning, but reversing the role of S and T's, we'll get that S is less than or equal to T. And because T is less than or equal to S and S is less than or equal to T, we will get that T equals S. Okay, so maybe you say that, okay, this is obvious, or this is trivial. Of course, if a series converges, then any rearrangement of this series will converge to the same sum. But be careful, this result is not true if you drop the assumption that the series is a positive series or a series of non-negative terms. Let's see an example. Suppose that shows you that the rearrangement of terms of the order of terms of a series is not a trivial thing. If we start with the alternating harmonic, the series we proved that its sum is ln2, series 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, etc. And we start by just multiplying every term of the series by 1/2. Then the new series, which is 1/2 minus 1/4 plus 1/6 minus 1/8 plus 1/10 minus 1/12, etc., will converge to 1/2 the sum of the alternating harmonic. And then we're going to insert zeros between the terms like this. Between the terms of this new obtained series, we're going to insert zeros. So we start with 0 and then take 1/2, then 0, then negative 1/4, then 0, then positive 1/6, then 0, then negative 1/8 plus 0 plus 1/10, etc. This new series with the inserted zeros will still converge to 1/2 ln2. Think about it, the partial sums of this new series will still converge to the same limit. Okay. Now why I'm adding the zeros like that? Because I will take this new series which I call double star, and I want to add it term by term with my original series, original alternating harmonic. So I get 1 plus 0 gives me 1, negative 1/2 plus 1/2 will give me 0. Term by term means column by column, like star and double star. 1/3 plus 0 is 1/3, negative 1/4, negative 1/4 is negative 1/2, 1/5 plus 0 is 1/5, negative 1/6 plus 1/6 is 0, 1/7 plus 0 is 1/7, negative 1/8, negative 1/8 is negative 1/4, plus 1/9 plus 0 is 1/9, negative 1/10 plus 1/10 is 0, etc. But when you add two convergent series, term by term, then the new series, the sum of the two, will converge to the sum of the two series. So the new series will converge to ln2 plus 1/2 ln2, which is 3/2 ln2. But now let's get rid of these zeros. If we get rid of the zeros in between, the sum will still be 3/2 ln2. And now we can see the series that we obtained more clearly. The terms is 1 plus 1/3 minus 1/2, plus 1/5 plus 1/7 minus 1/4, plus 1/9 plus 1/11. If I continue here, the next term will be 1/11, then negative 1/6. And let's compare the series 3 with the original series alternating harmonic. We see that C3 is just a rearrangement of 1. 3 stars here, so just rearrangement of 1 star. Because you take the first two positive terms, then followed by the first negative term, then the second two positive terms, 1/5, 1/7, followed by the second negative term, then the third two positive terms, 1/9 plus 1/11, followed by the third negative term, negative 1/6, etc. So 3, which is whose sum is 3/2 ln2, is just a rearrangement of 1 whose sum is just ln2. We rearrange the series, the terms of a series, and the sum got mysteriously multiplied by 3/2. So this tells you that we have to be careful with rearrangement of terms of a series. It's if we have a positive series that converges, yes, any rearrangement will converge to the same sum. But if we have a series whose terms are both positive and negative, then we have to be, there's a lot more to say.